Hello everyone, welcome to my channel. Myself Vignesh Anand. In this video we are going to see about the Thyristor and how the Thyristors are working and their advantages and disadvantages like that. So normally Thyristor in the sense it's also known as a silicon controlled rectifier. So it is a normal rectifier which converts AC to DC. So it is like switches. It will controls output power of a electrical circuit by switching on and off of your load circuits in a time given time interval. So this thyristor is a unidirectional semiconductor solid state device with four layers of alternating p and n type material. It consists of three electrodes: anode, cathode and a gate. So it is a combination of two diodes, we can say like that, with p and n junctions, like p n junction, then another two p n junctions. Then the anode is a positive terminal, cathode is a negative terminal, the gate which controls the current flow between the anode and cathode. So it is an electronic device and equipment to control your electric power or a current. It acts as a rectifier and can only transmit a current in a one direction only. Next we will see the short circuit diagram of your HVDC station. So in here the converter transformer uh, which gives the input to your 12 pulse converter, which is known as your rectifier or thyristors. This AC supply which comes from your converter transformer, it will gives to your thyristor, and the thyristor will converts it into a DC, and the DC will further moves to your load end. This is your overall HVDC station. We will see the particular uh, thyristor valves or that valves which converts your AC to DC. So this is your converter transformer, star delta and star star converter transformer. In here we have a thyristor valves, which is a series of thyristor connected with uh, your converter transformer for converting this AC to DC supply in your HDC station. This is one of the best example for your thyristors which used in your substations. Next, coming up to the thyristor diagram. So as I said, the thyristor makeup in the sense the thyristor common diagram: anode, cathode and gate, three connection points. Here the junction J1, J2, J3 will be in between your P and N junctions. How you can say. So here the p type semiconductor and n type semiconductor, then it will forms a diode and another set of diode, p type and n type semiconductor, which forms a thyristor makeup. Then the thyristor equivalent for a two transistor model also been given here. This is also one of the best example for your AC to DC conversions. Then the thyristor symbol is like a anode and cathode connections, anode, cathode and gate connections with a small triangle symbols. Then coming up to the explanation diagram, here as I said, the junctions J1, J2 and J3 in between your P and N and N and P, then P and N junctions. Here the junction J1 and J3 will be remains as a forward biased, and J2 will be remains as a reverse bias, because for example, for understanding I am saying that J1 junction is between your P type and N type. So starting will be P and positive, and ending will be negative. So for J3 also same, starting will be your P type and ending will be your N type. But in J2, starting will be your N type and ending will be your P type. Next is your two transistor type of thyristors. So in here the PNP and NPN type of transistors has been used. So normally the transistor which will having a two transistor equivalent circuits of your SER, and this is the connections for those SAR models. In this video we are going to see about this thyristor with a PN type of connections only. So in further videos we will go for studying of two transistor types also. This is your commonly used HVDC type of thyristor in HVDC stations. Next, coming up to the working. So when the anode is at a positive potential with respect to cathode, no current is applied to your gate. So the junction J1 and J3 will be forward biased condition and J2 will be in a reverse biased condition, as I said in the diagram. So no conduction will take place here. When the positive potential is increased beyond the breakdown voltage, which means the breakdown will occur at your junction J2 and starts conducting. Once the breakdown has been occurred, it will continuously conducts irrespective of your gate voltage. So until this potential of your anode is removed or a current flowing is cut off, so until that the conduction will take place. In order to control, we need to give a controlled voltage and controlled kind of thing. So in this case we are coming up with the gate voltage controllers. Next, when a positive potential is applied at your gate terminal with respect to the cathode, the breakdown of the J2 junction take place to switch on the thyristor quickly. So the gate act as a controlling electrode when a small voltage known as a gate pulse is applied to your gate. So it will triggers your thyristor to a conduction state and it will continue until the voltage across the device is reversed or it get removed. So commonly we are going to use this gate for controlling your gate pulse for controlling your thyristor input and output. Then VA characteristics. The thyristor, there are two types of VA characteristics. One is your thyristor in forward biased condition and second one is your reverse biased condition. First, forward biased condition. When anode is made positive, the PN junction at the end of your uh, thyristor will be a forward biased and center NP becomes a reverse biased. So it will be in a off condition till the gate current or gate pulse get induced in it and it will goes with a forward biased conductions. This triggering of your gate pulse through a gate current pulse, first one, when it is triggered by the gate current pulse, it starts conducting and act as a closed switch. So the thyristor will be remains on or until unless the latching state reduced to your holding stage. So next is your forward breakdown voltage. When forward voltage is applied on your gate, the leakage current starts to flow on your J2 junction in the middle junctions of your thyristor. So when the voltage exceeds the forward break over or critical limit, the J2 which means your second junction 2 will get breakdown and conduction starts place. Here when the gate current is increased, it reduces the blocking area and so the forward breakdown of your over voltage is reduced and it will turn on with a minimum current called as a latching current. So when the gate current Ig is equal to 0 and the anode current falls below a certain value called as a holding current, which means it will holds and there will be no conduction takes place during on that state. These two are main two conduction path. Then thyristor in reverse biased state, if the anode is negative with respect to cathode, with this application reverse voltage, which means the total system will be in a reverse condition. Both PN junction and J1 and J3 junctions will become reverse biased and the center J2 junction will become a forward biased. So only a small leakage current flows through it. So it will the thyristor will be in a remains as a blocked condition only now. So when the reverse voltage is increased further, then beyond the certain limit, the avalanche breakdown will take place and the J1 and J2 occurs, which means due to this avalanche breakdown, it will start conducting in your reverse direction. So the maximum reverse voltage at which a thyristor starts conducting is known as your reverse breakdown voltage. Now we will see one graph for example. So this is how the reverse and forward breakdown takes place. Here the conduction, in the sense the forward conduction on states, uh, the latching and the holding current is given here. Then the reverse current, reverse blocking has been given. So for a certain period it will be become a it will be in a reverse condition. Due to this avalanche breakdown, it will flows through your reverse conditions also. So here the gate current and the gate voltage also been shown here. These are all the VA characteristics of your thyristor. Next, modes of operation of your thyristor. Forward, there are three types of modes: forward blocking, reverse blocking, and forward conducting mode. Forward blocking, in the sense, before the forward breakdown takes place in your thyristor, that state is your forward blocking mode. In this state, the forward current conduction is blocked. The upper diode and the lower diode are in a forward biased, and the center J2 junction is in your reverse biased. Thus, the thyristor does not turns on because the gate pulse or the gate voltage or current which is not triggered in your thyristor. So there is no flow in your uh, conduction path. It will not form a conduction path actually. Reverse blocking, this is your reverse breakdown. Before the reverse breakdown takes place, the conduction of your anode and cathode is reversed, and still no current flows through it. The thyristor can conduct a current only in one direction, and it blocks in a reverse direction, so there is no flow of current. Next is your forward conducting state, which is after your forward breakdown takes place in your thyristor. So when a current is applied to the gate, the thyristor got triggered and starts conducting. This stays up till the forward current drops, or the threshold values achieved is lesser than the value, and got turned off. So these are all the understandings. The thyristor blocks a voltage in both forward and reverse direction, and thus a symmetric blocking is formed. A thyristor turns on by the application of giving a gate current or a voltage, and turns off when the anode voltage drops to zero. A small current from the gate to the cathode can trigger the thyristor by changing it from a open circuit to a short circuit. So these are all the understandings from the VA and the before thyristor and the modes of operation. There are different types of thyristors based on your turning on and off capabilities, and then their physical structures. So normally silicon controlled rectifier or thyristors commonly used in your all of most of the areas. Then the emitter type of thyristors, fast switching thyristors, then light achieved silicon controlled rectifiers, then gate turn off thyristors, reverse conducting thyristors, FET controlled thyristors, MOS turn off thyristors, then bidirectional phase controlled thyristors. So these are all the common types of thyristors used. In coming up video we will see this elaborately. In here we are going to see now continuing with the silicon controlled thyristors. So when connecting with the system, we need a protection for these thyristors. In here we have two types of protections. One is di by dt, then another one is dv by dt, which means rate of change of your current and rate of change of your voltage. Here the rate of change of current, the thyristor need to be protected against your fast rising current spikes. After switching, it requires a minimum time to establish your current uniformly through your all of your junctions. Otherwise, the fast rising current during your switching may damage the junctions, may give some excessive heat or a short circuit within your junction itself. In order to overcome this, we are going to connect a reactor or a inductor in series with your connections. So this is your connection of your reactor in your thyristor circuit for di by dt protections. Then coming up to the dv by dt, which means your rise of rate of voltage, fast rising voltages between your anode and cathode of your thyristor. So whenever turning on, uh, the sudden spikes of your voltage will be occurring. So we need to reduce these sudden spikes or switching surges. In case if you use a capacitor and a reactor, sorry, resistor in a parallel with your circuit, means it will limit your fast rising of your voltage. The capacitor will charge and it will discharge when the thyristor is turned on. To limit the discharging current of your capacitor, a resistor is used in series with the capacitors. So this overall circuits will forms a suppression of your suppression circuit. So it is commonly known as your snubber circuit in your thyristor connections. This is your snubber circuit connection in your thyristors. Next, coming up to the application of your thyristors. So mainly it is used in your variable speed motor drives. Then it is used for controlling your high power electrical applications. Then used mainly in your AC motors, lightings and welding machines. Then used in your fault current limiter and circuit breakers. Then used in your fast switching speeds and low conduction in is possible for in a ETO type of thyristors. Then it is used as a dimmers in your televisions, movie theaters. Then in photography for your flashes. Then can be used in your burglar alarms. Then used in your electric fans switch, which means speed controls. Then it is used in your car ignition system switches also. So these are all the commonly which means the all the type of thyristors which I have earlier explained. Thus this is your application of your all those thyristors. So hope you all understand. I think so. See you in next video. Have a nice day. Nandri, vanakkam.